Hello and welcome back to the Oxford Online Maths Club. I missed my mark a tiny bit there. I don't think anyone noticed. My name's James and I'm joined this week by Gaurav.
Hello.
Gaurav, you're a current student. What are you currently studying?
So I'm a first year undergraduate, currently going through my maths degree,
Fantastic. Good. Which college are you at?
and I'm a Pembroke College.
Very good.
So
Cool. Okay. And we've got people watching at home as well. YouTube tells me there's quite a few people, and they're joining Slido as well. For example, here is Jonathan, who says, hello. Hello, Jonathan. If you'd like to join Slido as well, like Jonathan has, you can do so over at slido.com/OOMC, which should take you to the correct Slido location. Or if you're at slido.com, I don't know if that's your homepage or something, put in event code OOMC, and that should be the same thing. I don't know. That's where we do things like ask for you to join in and interrupt us. Unlike your maths class, you're maybe unlike your lessons in school, you're encouraged to interrupt and join in and ask us to say things again. Look, so here are people joining, Enora and Joe and an anonymous person. You can be anonymous in this chat. Chat today is being moderated by Mario, who is a DPhil student at Oxford as well. Good. There you go. Thank you, Mario, in chat. Good. There's more anonymous people. Lovely. I would also like to know how their day is. The Slido is where I can run polls like this. Let's do this one. Hang on, I've made that poll way too tall. Sorry, Gaurav. I normally set things up just right beforehand with no problems. That's not true at
yeah,
all.
no, it's fine. Like I can see the poll.
You can see that poll? Yeah, good. So they're
Yeah,
having an okay day, I think. What was it kind of 3-star, 4-star, 5-star kind of day? How's your day going on a scale from 1 to 5?
it's a fairly busy day, but I'd say it's a 4. Um,
4 is pretty
Pretty
good.
good.
I'd take a 4. I think most days. Sometimes I feel like chat will as well to join in on a 4. Yeah, it's been very busy and it's still very cold, isn't it? Maybe that's
Yeah, yeah. I didn't need to go to lectures wearing a jacket every morning. Like I did, but usually it was fine. But nowadays, I find even with a jacket, I'm feeling slightly chilly.
Yeah,
So
I know. I've got hats and scarves over the side. Someone's just clocked in to say they're having a 2-star day, which is not great. I sort of wonder whether, 2-star day, but maybe some maths. Maybe maths is the answer. Quick,
maybe this will make it better.
maybe, yeah, sure. If you would like some more maths outside of this stream, we're going to do our best to give you some maths for the next hour. But if you want more than that, then here are some places where you can find more maths. The Promise Europe Summer School, which I've mentioned every week for a few weeks, is a source. Obviously, for people who go on the summer school, they get loads of maths over the course of 6 weeks. But even if you don't go on the summer school, they have some hard problems for people to try. Always a fan of hard problems. Other things I should mention are the Maths Institute has some warm-up problems for people starting a maths degree. If you're watching this in year 13 in England or equivalent, because you're about to start university, then we have these kind of practice problems for people bridging the gap to university. Did you have a look at these this time last year, Gaurav? Or,
I was considering it. Like, I did actually look at Promise. I ended up not applying because I had some stuff going because I think for this application, is it the one where you need to submit a few questions beforehand? Like you have a month to do a couple of questions?
Yeah, they have a worksheet of 10
Yeah,
questions.
yeah. I looked at that and I found it quite challenging. And I had some other things going on at the same time. Like there was this other online course I was doing at the same time, which was a little bit like I was doing like 2 online courses at the same time, and that was a bit demanding. And I didn't know if I would have time to like properly spend on doing this worksheet. And I also didn't know if I wanted to do a third course on top of what I was already doing. So
There's there's a lot of
yeah,
other
I
maths out there, isn't there? For example, look at this segue. For example, we've been doing this this year for 6 weeks now. So if you've just joined us for the first time today, look at that! It's an array of pink rectangles. These are previous episodes just from this year, and we're closing in, I think, on about 80 episodes of Maths Club total. If you scroll back through previous years as well. This year so far, we've had episodes on maths and music last week with Maria. I thought that was really good. Just before we went live, we were talking about music theory and maths. Sergey was on before to talk about the foundations of computer science. We've had Puzzles from Jane Street, who support the show. We've had Integration with Beth, Jack telling us a theorem from Futurama. So if any of that sounds interesting to you, that's just what we've done this year so far, about 70 or 80. Yeah, Jay thinks Automata has been best so far. I'm going to pick out a particular thing from the music theory episode. I should say each of these previous ones from this year has got further reading. I'm quite proud of some of the bits of further reading that we've put together. I'm quite proud of. I just want to make sure people have seen them. For example, one of them has a follow-up question from the music theory episode. So last week we saw this briefly, and one of the further reading pages has a kind of follow-up question to think about what happens if you sort of join the dots for these notes. What's going on here? This is the harmonic series from last week. These notes follow a simple rule, and there's something going on here on the music stave. I don't know if anybody had a look at that in the further reading last week. If not, then hey, there's more than that. We've got, I think last week was a particular highlight. We had about 20 links to other stuff. Not all of it maths and not all of it homework content, but about 20 external links. We also set puzzles and problems sometimes, and in fact it's one of those puzzles or problems from the winter puzzles episode that I want to talk about today. So I've got Gaurav on the stream to help talk about this particular problem. I'm going to try and talk about this one, but don't worry, if you haven't seen it before, we're going to give you some time to think about it before we give you the spoilers, give you the answers to this one. Okay, I also think we should get into this maths. We've got people in chat having about a 3.9 sort of day, which is pretty good. Let's see if prime numbers will step that up. Cool. Just to check, Gaurav, can you see this over the call? I'm going to read it out.
Yeah.
Okay. Cool. Right.
Yeah, I can see the questions. Yeah.
Or maybe can I get you to read out this first one then?
Sure.
Just here.
All right. So the question is: suppose p greater than 3 is prime. Prove that p squared minus 1 is a multiple of 12. And a hint: the lenses are something to do with 2 and something to do with 3.
Yeah. So this is.
I see. So like you can approach this question by looking at essentially, like divisors by 2 and divisors by 3. So maybe that might help with the approach.
Yeah.
And there's a follow-up question, which is to.
Well, let's pause before we do follow-ups.
The
context for lenses. Sorry, I should have said that bit first. The context for lenses is from an episode about a month ago where I tried to explain this idea about looking at the same problem from 2 different angles. Like you've got 3D glasses in the cinema in the old days. Oh, nobody knows this, but like a red lens and a blue lens that let you see different things about the problem. There's some things when you look through the red lens, there's some things you can't see. And when you look through the blue lens, there's some things that you can't see, kind of limiting what you can see. That was the context for the episode previously, looking at the puzzle in different ways like that. So this is a follow-up from that to look at the problem in different ways. And you've added this word divisors, which people might or might not have met. So maybe that's a clue. But I suppose it's linked to this idea of multiples, right? So if I was describing, maybe this is a hard question, but why did you say divisors? Why were you thinking of divisors?
Just because if something is a multiple of another thing, it means it's like divided by something. So like, for example, I guess 24 is a multiple of 6. That's another way of saying 6 divides 24 evenly. So they're both like related concepts. And I think in a way, they're like something being divided by something else usually gives you more information than it being a multiple of something. Okay.
Okay, I've made some notes down the side of things that you've said about like other concepts that you're thinking of when you see multiple, because I think that's a good problem-solving sort of strategy to take a word in the question and think other related concepts. We could play the same game with the word prime. I'm kind of assuming that people in chat know what a prime is, but let's remind ourselves. What do we think of when we see the word prime? I guess I'm doing that as a question, possibly for chat. I guess chat can definitely give me the definition of a prime, so I'll let somebody in chat tell me what a prime number is. But then the harder question is sort of, what are you thinking about when you know something's a prime? What kind of concepts do you have? What's your toolkit of things to work with when you hear that p greater than 3 is a prime number? What have we got? Cool. So Joe in chat says that primes are only divisible by 1 and itself, which is pretty good. An anonymous person is also typing. I do like getting multiple people in chat. So even if someone else has typed a thing and you're typing, just go for it. Yes, thank you. Right, okay, let's give them a second. Because I suppose the dream for problem solving, right, is that you look at the given information and you look at the place you're trying to get to and you find a connection between those facts, right? So yeah, here we go. Chat is giving us definitions of primes. Can you also give us some sort of what's the connection? What's the kind of thing that your definition of prime, which I agree with. I like your definition of primes. What's the thing that they've got in common with this kind of with the other end of the problem? It's multiples of 12. I just asked that like it was a good question, but I've realised that you could just say a prime is not a multiple of 12. Which is kind of a true fact, right? What I'd like to get to is this kind of distinction about true facts and helpful facts. They're sort of different. Like primes are not multiples of 12. True fact. Is it helpful? Not sure. I guess p squared is also not a multiple of 12. Yeah, probably. Is this helpful? Not sure. And it's much easier to come up with kind of true facts working forwards, and I suppose helpful facts working backwards. So starting from where you're trying to get to and work backwards. Am I making sense? I'm not sure. Is this a tactic that you've used for questions before? Ooh. I was like, maybe not, and I think I just lost your audio for a second. So
can you still hear me?
Yeah, I can now. Sorry.
Yeah. No, I was just saying, like with problem sheet questions, sometimes when I have absolutely no idea what's going on, I just write down everything I know. So especially with analysis, that tends to happen a lot. So I just write down, oh, I'm told that this series converges, which means this, or this thing is bigger than this, which means I can say this. I just write down all the information I have, and sometimes that's enough for me to piece it together.
Yeah, I'm smiling because we've all had problem sheets like this where you just write down what you know and hope for the best. So you're like, so here I know what a prime number is, so maybe I'll write that down. So somebody in chat, anonymous, says 12 is a combination of 2 and 3, which is quite a good fact. So maybe we can attack this by thinking about multiples of 2 and multiples of 3. There's a missing ingredient, there's a bit we haven't really thought about, which is this p squared minus 1. So I'd quite like to understand p squared minus 1. I haven't really thought yet about the fact that p is greater than 3. So yeah, the missing ingredient, I think I need to think about p squared minus 1. Here it comes. So one of my favourite tricks is difference of 2 squares. Let's see if chat has what difference 2 squares. Yeah. If my connection is not great over we're on a Zoom call. It's doing okay, I think. I think we're back. Good. Okay. If you drop in and out, I will keep talking about prime numbers in between.
Okay.
I'm just going to keep saying the same things about prime numbers. Okay. Keeping up. Good. Yes. Yes, it is helpful, I think, to know that p squared minus 1 is different to 2 squares because, as Guruf says, knowing stuff is helpful because you can write it down. I suppose I don't know yet whether this is helpful, but I do know that it's true. And you should not let concerns about being helpful slow you down from writing down true facts. Your goal is to write down facts that are true and helpful. Writing down true facts is sometimes the best you can do. Yes, so multiples of 2 and 3 then. Possibly we should look at these different brackets and think about whether they're multiples of 2 or multiples of 3. At this point, the question just falls over, and once you've started thinking about the brackets there, and thinking about whether they're multiples of 2 or 3, you're kind of almost immediately done. Yeah. So thinking about multiples of, should we do 3 first? So multiples of 3, there's a p minus 1 and there's a p plus 1. We'd like this to be a multiple of 3. We've got to remember where we're going. We'd like this to be a multiple of 3. So ideally, our argument is going to be something like one of those brackets is a multiple of 3. Obvious question, which one? Throw to Gaurav. Which one is multiple of 3?
Well, that depends on what your P is.
Yeah, I thought it'd be a good question, but then it turns out, oh no, it's not the case that like one of them is always a multiple of 3 and the other one isn't. It's like, it depends what P is. Okay.
I guess, yeah, thinking about it in terms of like what multiples of 3 look like, maybe that might, or how you can represent every number as some multiple of 3 plus something else. Maybe that might help some people think about how to approach this.
So I like those kind of routes where you might think about remainders. In chat, in chat there's some chat about odd and even numbers that I want to do in a second, of course, and some things about remainders when you divide by 6. So there's a 6n plus or minus 1 in chat, and there's a suggestion to start from 5. And I wonder whether that person is imagining that we do some sort of induction or something. To start from 5, you've got to start somewhere. Why not start from 5 and then see what happens? I suppose if you put 5 in, it's good to have an example, isn't it? So if I put in 5, I'm not saying that P has to be 5, but just as an example. Yeah, okay, so I get 5 plus 1 is 6, is a multiple of 3. And the other one in this case is not a multiple of 3. Okay. So yes.
And then I guess if you pick 7, then you get the opposite example where 7 minus 1 is a multiple of 3, but 7 plus 1 isn't.
Yeah, okay. I think we've got to the point where some people in chat, possibly everyone in chat, has worked out what's going on, but I'm going to draw out the point a bit because in a second I'm going to show you approximately 20 of these. I want to really understand what's going on in this one before I show you 20 others. That's the plan. Okay, yeah, so it might be the first bracket or it might be the second one. One way to imagine this is that multiples of 3 occur on the number line like every third one, like this. That was such a stupid way of saying it, but multiples of 3 appear every third number. So if you have 3 numbers in a row, you always have a multiple of 3 somewhere in there. And why am I thinking about 3 in a row? Well, I'm thinking about p minus 1 and p plus 1 being 2 elements of that set, I suppose. Maybe nobody in chat is thinking like this. I think maybe Gaurav wasn't thinking like this, but that's okay.
No, I mean, I was pretty much doing exactly that. Just yeah. It helps if anyone in chat knows what modular arithmetic is, then it's a very similar idea to that. But in case you don't, the ideas are fairly it's just about deconstructing the problem into what you know. That's just essentially what all of math boils down to.
You mentioned modular arithmetic because I can now do a great ad, because next week, I don't normally tell them what's coming up next week, but next week we've got modular arithmetic. So we're going to do lots of what's the remainder when you divide something, or what's the equivalence class when you divide something. To look at a way of focusing on a particular aspect of the number line. Anyway, that's next week. So this week, whatever you're doing, one of those is a multiple of 3 because the number in between, p itself, isn't a multiple of 3 because it's a prime. And that was the thing you know about primes. Oh, prime's larger than 3. There it is. So knowing that it's larger than 3 tells me that I have a prime here that's not a multiple of 3. So if it's not a multiple of 3, something on either side must be. Chat has also told me that if you think about this mod 2, or if you think about even and oddness, or parity, we sometimes call it, then, well, even numbers appear every other number, and p is not even. So actually both of these are even, which gets you a multiple of 2 here and another multiple of 2 there. So because they're both even, let's write that on the screen. Both even. Aha. That gives you a multiple of 4. Cool. Yes, p is guaranteed to be odd. Here's an anonymous person. Brilliant, love it. Guaranteed to be odd, therefore p minus 1, p plus 1, both even, and therefore it's a multiple of 4. Good. Nice. Happy? I think we've done that one to death. I could tell I was doing it more than chat wanted, I think. Do let me know if I bored the socks off. Well, I suppose let me know if I haven't bored the socks off anyone, because that was my intention. It can be more boring. Because now I want to take that understanding that we have and try and do the follow-up question, right? Time to read the follow-up question. Do you want to do the honours? So follow-up question. Oh, I've lost your audio just at the moment I put you. Sorry, I'm so sorry.
Now?
Yep, back again.
Okay. Yeah, the follow-up is suppose p greater than 3 is prime. Prove that p squared minus 1 is a multiple of 24 now.
Yeah. So the same setup to the question, but then just a stronger punchline. That p squared minus 1 is a multiple of 24. Similar question, I guess. Someone in chat says, why is p guaranteed to be odd? And Treya says, because p is prime, so it's odd. I suppose there is a way to make that into 2 steps of argument, right? Like, why are primes odd? But depending on who you're explaining it to, you might have more or less steps in your argument. There's something going on there. Anyway, I think it's a good explanation. P is prime, so it's odd. Well, I suppose. And it's not 2.
And it's greater than 2, yeah.
As we always say, 2 is a very odd prime. Right, anyway, so don't laugh at that. That joke's older than all of us, right?
That's new to me. Yeah.
Suppose p greater than 3 is prime. This time we're going to show that it's a multiple of 24. Of course, we don't want to start completely from scratch. Hopefully, not guaranteed, I suppose, but hopefully it's relevant that we already know that it's a multiple of 12. So hopefully we can use that fact, or at least use the ideas behind that fact. I don't know. What does chat think? And what do you think? Where's Eddie? Eddie's coming in with a kind of steel chair. Eddie has checked that it works for 5. And now I suppose is claiming that it keeps working. And they're right, it does keep working. I'm not sure I understand. Probably Eddie has a thought process behind that as well that I haven't quite understood from the chat message. Yeah. Okay, more stuff. Give me more. Our success last time was thinking about 12 being 2 times 2 times 3 as a kind of to-do list to say, okay, we found a 3. I think I talked about that one first, and then we talked about some 2s. We found 2 of them, and then once we'd got there, we had a multiple of 12. I guess my optimism here is to do this as a kind of checklist to say, in order to prove that something's a multiple of 24, you can prove that it's a multiple of 3 and that it's a multiple of 8. I guess you have to be a bit careful. I'm writing down all these 2s. I'm relying on the idea that they're separate 2s. Like, it's not okay to prove that something's even and then prove that it's even again with a different proof, and then say, aha, it's double even. I proved it twice. So therefore it's a multiple of 4. That's kind of, these need to be different factors of 2. So here, this one's even, and also the other bracket is separately even. So there's kind of separate factors of 2. The mistake that people make sometimes is just sort of adamantly prove, like, rewrite my working and now it's multiple of 16. Like, something gone wrong. Good. Tim, in chat, what does Tim say? These are two adjacent evens. This is a language. If I'm being, the obvious follow-up question, I think, is what do you mean by adjacent even? I kind of know what you mean. They say that every other even number is a multiple of 4. So thinking about these two numbers.
I think that's probably the best way, or at least that's the way that came to me first as well. Thinking of it that way, in terms of consecutive even numbers.
Yeah.
Maybe that might help.
I suppose that's the bit of the argument to look at, and part of the strategy here is not looking over here at the multiples of 3, but looking at the evenness again to try and do better over there. And you're remembering that you're looking for another factor of 2 this time around, because there's sort of an extra factor of 2. I think that's why you would look over here, and then your argument is going to be something like, yeah, well, they're both even and they differ by 2, so one of them is secretly a multiple of 4. Yeah, and somebody else in chat is just a consecutive evens question mark, and I'm not sure whether they mean James and Guruf, does this work because they're consecutive even numbers question mark, or maybe they mean Tim, what do you mean by consecutive evens? Possible, right? I'm gonna draw a little number line just in case. I don't know. Maybe this is unnecessary.
I mean, I think I understand what what Tim is trying to say.
Yeah. Evens. Oh, handwriting. Evens. And then maybe this is the picture for consecutive evens, one after the other in sequence 2, 4, 6. Every one of these is sort of double even. I've said that really badly. Why would I say sort of double even? That's like even more words with a weasel word in the middle. It does actually work. If you draw yourself a sequence like this with every 4th dot coloured in to think about multiples of 4, or maybe if you do modular arithmetic mod 4, then you can make that work, I think. Think about where p lies relative to multiples of 4. There's only a few possibilities, right? Is your prime a multiple of 4? Probably not. Is it 1 more than a multiple of 4? Maybe. Is it 2 more than a multiple of 4? No, because then it'd be even. Is it 3 more than a multiple of 4? Maybe. Is it 4 more than a multiple of 4? Well, that's the same thing as the first thing. If you're 4 more than a multiple of 4, you're a multiple of 4 again. So now we're round. So there's the possibilities. In each case, one or the other of these is a multiple of 4. The other is a multiple of 2. Aha, consecutive. That's a keyword as well. Good, right. Listing out different words. Good. Okay, so I think they've convinced me that this one is a multiple of 24. Well, the same expression. And that this was useful, helpful along the way, but we could actually prove something stronger. So my plan for this, and this is a little bit experimental, is to try and explore the question, where's the limit? How far can we push that? I have a chart for this. Right. Let's see if this works. I think it's over here somewhere and down a bit. Yeah, here it is. Here's my chart. Right. Behold. So if I zoom in, I can look at particular bits of this chart. So here's the first statement we had. Multiple of 12. And we've decided that this one is true. And then there is a logic to the layout that I'll explain in a moment, but we've just thought about multiples of 24. And I've got other numbers. So I've got lots of other facts in a kind of grid. The logic for this is that, zoom out a bit, going from left to right, I have stronger hypotheses. The hypothesis in each case is stronger. So over here, strong, and on the left, weak. And this direction is about the hypothesis, the kind of assumptions that you're making about the number. So this is kind of the hypothesis direction. hypothesis has got several meanings, I suppose. It's also used in statistics, and it's also used in a kind of sense of something you suppose to be true, but here I'm using it to mean the kind of first half of the sentence, the bit that says if. Going from left to right, and going up in this direction, on this axis, I have conclusion, which is the word for the thing that you get, but it starts with then. So the kind of second part. And I have weak conclusions, so just sort of rubbish conclusions like, oh, p squared minus 1 is a number. And I have stronger conclusions up here, where, like in our previous example, we went from a kind of relatively good conclusion to a stronger conclusion. Going upwards is stronger. So from left to right, weak hypothesis, just assuming almost nothing, to, on the right, strong hypothesis, assuming quite a lot. My groups here are p is prime. In the middle I have p is prime and also p is bigger than 3. And on the right I have p is prime and also has last digit 1 or 9 in decimal, in case anybody's asking. And then going up I have p squared minus 1, multiple of 1, 3, 12, 24 or 120. This is my crazy picture. In we go. So the question I suppose is, can I push this further? I've picked the number 120 as the kind of next number that we might think about. And this is either true or false. Let me know in chat what you think about that fact. If p is prime and p is greater than 3, then p squared minus 1 is a multiple of 120. Right, and I'm going to catch up with chat. Yes. Yep, good. What's the difference between a hypothesis and a conjecture? So the hypothesis is the bit on the first line. It's the bit that says if. It's the kind of input. And then the conclusion is the output. It's the kind of result that you get afterwards. I might have said conjecture at one point, and that was not the right word to use, sorry. In maths, conjecture is something that you haven't proved yet. For example, that whole statement at the top, the whole thing in the box is some sort of conjecture. Might be true, might be false.
Right.
So we're looking up here. I've got a lot of facts now, maybe an overwhelming number of maths facts. Warning, some of them are false. What do you think about this one? I'm going to put Gaurav on the spot. People in chat have got opinions.
Well, I think I'm going to go with false. And I guess a preliminary check is just, if you pick p equals 5, then 5 squared minus 1 is already smaller than 120, so it can't really be a multiple of 120.
Yeah. 24 is not a multiple of 120. And in maths, just one counterexample is enough. It is now dead, it's false. People in chat are also checking sort of 7, and it doesn't really get better from here, but yeah, like 7, no good. 5, but just a single counterexample is enough to kill this. And say that's not true. So something I'm interested in is that we crossed the kind of boundary, right? We were trying to make stronger and stronger conclusions, but we crossed a kind of boundary around here somewhere. There's a lot of numbers between 24 and 120, but maybe around here somewhere there's some sort of boundary that we crossed. And this boundary in general it sort of tends to slope upwards from the bottom left to the top right of this picture. So we're going to explore to try and find out where it is, but the general thing I think I want you to take away from this is that the stronger your input, the stronger your output. That if you assume quite a lot, then you should be able to prove more. It doesn't always work out like that, but if you have more conditions in the if part, then maybe you can get further. Okay. Yes, people in chat are saying P must be a multiple of 5, which is an example of trying to strengthen the hypothesis. Oh, I'm going to get it wrong at some point. I'm going to get it mixed up. Either by saying weak when I mean strong, or strong when I mean weak, or by saying hypothesis when I mean conclusion, or conclusion when I mean hypothesis. think I'm doing all right so far. At the moment, all of these have the same hypothesis. In this column, I have more in this column. My plan is that the column is all the same hypothesis, and the row is all the same conclusion. With, of course, disastrous consequences. Like, a lot of the things I'm about to show you are false. But I'm considering a big chart of, in theory, all possible inputs and all possible outputs. Probably for this chart today, just related to prime numbers and whether or not they're multiples of stuff. But I think you can play this game for kind of any maths fact you like. Okay, so we found a boundary here. I'm going to go down. Going down, you get these facts down here. So these ones are true. We actually already proved this one. If p is prime and p is greater than 3, then p squared minus 1 is a multiple of 3. So that one's true. And in fact, it was helpful along the way when we were trying to prove this fact about being a multiple of 12, I think. Is that fair?
Because, I mean, if it's a multiple of 12, then it has to be a multiple of 3, right?
Yeah.
And you could go the other way as well. Like, if it's not a multiple of 3, then it definitely is not a multiple of 12. So, like, the converse is also true. So I think that's very helpful.
Yeah, so there's kind of implication arrows that you can draw in here. I don't really know if everyone has seen these, and I'm not a massive fan, so I'm not going to be drawing them on my diagram. I'm a fan in some situations of writing down the implication arrow, but some of these facts imply other facts. Maths is mostly about consequences. Down here I've got an example of just a really terrible conclusion. So it's like a bad joke, right? With loads of setup and then no punchline at the end. Like if p is prime and p is greater than 3, I'm listening, tell me more. Then p squared minus 1, an interesting calculation, is a number. So, true, I guess, but not fun. So kind of your job as a mathematician, I suppose, if you're trying to prove facts, is to try and move up the picture, because the facts get more interesting the higher you go, you're proving more stuff, and to try and move left, because if you move left, you have fewer assumptions. Yeah, good. Yeah, so people are telling me about p being even. Right, so there's this p greater than 3 thing in here. I want to take a little look to the left, where I've tried weakening the hypothesis. So in this column it all says if p is prime, then p squared minus 1 is a multiple of 24. And this is an experiment to see, well, did it matter that I said p was greater than 3? How much does it matter? So looking in this column, where's the truth boundary? Where does it switch from being true to false? Good, right, I'm going to let chat have a think about that. I think I'm going somewhere with this. I'm not certain. I've never done this before. I've never shown people the kind of chart. This is a new experiment in trying to visualize where the line is between truth and falsehood. I think it's a bit of a disaster, really, if I remove this condition from the hypothesis about p being larger than 3, which we will find out in a second.
And I think, just in case people are wondering about it, 1 is not prime. So please don't try to do it with 1.
Well, yeah.
I mean, to be fair, it still works, actually.
Is that relevant right now? Are we getting close to we're getting close, I think, to the true fact. If p is a number, then p squared minus 1 is a number. Very weak hypothesis.
Yeah, no, I thought I was going somewhere with it, and then I realized that it doesn't change anything at all. So it really doesn't matter.
Can the multiple number be a fraction? No. So when I say a multiple of 3, I mean something, right? I mean you're multiplying 3 by a whole number to get to this, in this case. So yes, if you're allowing fractions, then kind of almost anything goes. So I think most of these are false. Yeah, integers today for our multiples. I found out some people think I found this out, that some people think all numbers are square. Are you aware of this kind of mild conspiracy theory?
I haven't heard that one before.
So once you found out about irrational numbers, like the square root of 2, you go, aha, now I've learned that 2 has a square root. I now think that 2 is a square number because it's root 2 squared. There's a mild conspiracy, but actually all numbers are square, except the negative numbers. But I don't think that's what people really mean when they say square number. When people say square number, they usually mean it's the square of a whole number. Yes, right, okay. Prime must be an odd integer, or 2. Don't forget 2. Very odd prime. Right, okay. People in chat, I can't tell if they've told me this or not, but this one is false. Just very false. I mean, it was false before. Your counterexample still works. So there's this tendency that because of the way I've set up my my hypotheses to feed into each other and my conclusions to feed into each other, because of the way I've set it up, things to the left of falsehoods are false, and things above falsehoods are also false. The kind of madness of wrong facts extends in this direction. Loads of false stuff. If I try strengthening this like 480, or if I try weakening this to say if p is a number or something, then there's got loads of not very interesting false facts. And in fact, these ones are also false. Is this one false? If p is prime, then p squared minus 1 is a multiple of 3. What do we think? So someone in chat says if p is prime and not 3, it works for multiple of 3. If p is not 2, it works for multiple of 8. Ooh. How are they getting multiple of 8s now? Oh yes, we had 8 before. 8 was part of the 24 argument.
Yeah.
It's me being slow about multiplication. Proof so many factors. This one's not true, because p could be 3. And this one down here is still true. So we have this kind of like truth boundary, which kind of separates off around here, and then snakes up here, and then joins up over there to kind of separate false facts from true facts. We've thought a little bit about this kind of horizontal bit of the truth boundary, where you go from kind of a conclusion that's too audacious, too strong. Like you can't do that. You haven't got enough information to conclude that. We've seen that up here, where 24, but don't get carried away. It's not a multiple of 120. Like, you can't just prove everything with that information. The vertical bit of the truth boundary separates things with different hypotheses. So here the difference between left and right is whether or not I add in this extra claim that p is bigger than 3, or extra bit of information. I've seen that described, by the way, as a kind of exam tip. I don't know if you can see what I'm guessing at here, but I think examiners like to ask questions that are near the truth boundary. That it's seen as poor form on the part of the question setter to ask a question where, so like down here, if p is prime and p is greater than 3, well, the greater than 3 isn't really doing anything in the question, because it would still be true if you moved one step left. Weaker thing. So I've heard this described as, do you know the kind of strategy I'm talking about? Or?
Not really.
Okay. So I've heard it described as make sure you use all of the information in the question. If they give you facts in the question, then it's for a reason.
Right.
Yeah, so 3 is a good counterexample over in this box, which usually works because
I would say that's usually very helpful advice.
We were talking.
Sorry, I interrupted you.
No, go. Yeah. Okay.
Oh no, I was just going to say that usually it's very helpful advice to use all the all the information in the question. But sometimes our maths teacher in school, he used to be a little bit sneaky, and sometimes give us information which we didn't actually need, and that sometimes made it a lot more difficult.
Yeah, I'm going to do that now. I'm going to give them more information.
But yes, in general, it's pretty good to.
Yeah, so I'm gonna try going to the right on this diagram to give people more information, which maybe makes the question harder because now there's like weird information that you maybe need or maybe don't need. If I go over here, I've added in this fact about the last digit. So replacing this thing prime greater than 3 by saying prime with last digit 1 or 9. So here we are. Yeah, it's a bit of a red herring. You can catch out small children this way. There's a test that they do for mathematical reasoning on children where you say, you set up a problem like a farmer has 8 cows and 16 sheep. How many dogs does he have? And the correct answer is, what are you talking about? I've no idea. The information is like not enough to get to a conclusion. But if you show this problem to small children, you say he's got 8 cows and 16 sheep or something?
Yeah.
Yeah. What do you think happens if you show this to small children?
They say 24.
They say 24. And some of them will say 2. Some of them will say 8. Because sometimes you learn techniques and you know that you have to do something with the numbers you've been given. So combining them together in some way. It's quite hard to say, I don't know, or the answer is just none of this. Right, people are tackling what's going on with last digit 9 or 1. There is some stuff about people are thinking about multiples of 10 and last digits, which is great. I was hoping that if I put the phrase last digit in, then people might start thinking about the last digit of this, right? P squared minus 1. Or I suppose factorise it. So you can still factorise it. Think about the last digits over there. So the question is, where's the truth boundary? So I suppose we're going to think about multiples of 5, because this 120 includes a multiple of 5, I guess, as well. And this is just one direction I could have taken this in. There are other directions I could go in. People in chat earlier were trying out different hypotheses, the different restrictions, because I think it can be quite annoying to see a fact that's like not true. You want to try and fix it. A phrase that I learned from actually the Promise Summer School have some questions of that format, where it says prove or disprove, so work out if it's true or false, prove or disprove, and salvage if possible, to try and rescue it, so that if it's false, try and find a true fact nearby. So when you see this false fact up here, a difficult problem is to try and find a true fact nearby. So maybe move down a bit and find a true fact over here, or maybe, I think people are there, move to the right and find a true fact over there. I think both of those skills are pretty tough. And that's why I'm trying to do truth boundary stuff. So think about where the boundary is. Maybe there's someone out there who likes to visualize things and having some sort of chart where you can say, aha, we have a region on our chart where things are true. And a region on our chart where things are false. And some sort of boundary in between. Yes. Yes, and because of the implications, so because I've set up my hypotheses to be related to each other, in the sense that if you have this hypothesis, then you have the one to the left, and then you have the one to the left of that, they're linked together. So if you find a true fact in this diagram, everything to the right and everything below it is also true. That's not true if you use like random facts in random places, but my hypotheses are linked together and my conclusions are linked together. Right, implications. Maybe I have to draw some implication arrows. 50-50, I get them the right way around. Can you help me? Which way round am I supposed to draw implication arrows?
For between like correct to false, or
Well, I think this fact here implies the one below it.
oh right, I
Because
see. Yeah,
I mean, like if
yeah.
so, if you're a multiple of 24, then you're a
But,
multiple of 12. Which
and same way you could like extend that arrow down pretty much all the way. That 12
yeah,
implies multiple of 3, and then yeah, well, is a number is implied by pretty much all of them. And then same with these ones. Yeah, all the implication arrows go downwards.
one of these is going to annoy people, I think. But so arrows crossing the truth boundary is going to be a thing that people want to talk about. But because I've set up my kind of implications like this, and I've got implications to the right, looking at my hypotheses. Once you get a bit of truth, you get a big green rectangle to the right and down. I'm trying to draw these kind of arrows with a double line to the shaft of the arrow, but a normal arrowhead, which is surprisingly difficult. Am I doing badly at this? Right, okay.
I mean, the stream quality makes it so that I can't tell.
Oh, sorry. Maybe I've got away with it then. Right, yes. Questions in chat. Here we go. Yes. There's an anonymous question coming that's the correct question to ask. This is exactly the sort of thing that I thought people would not like. And it's really like this one crossing the boundary that I think people will be annoyed by. So someone says, why would you put implication arrows between incorrect statements? It's a good question, right? Do you want to have a go at it? I can do it afterwards if you like.
Sure. I mean, I think if you can think about it in the way that what an implication arrow means is if you have A right implication arrow and then B, what that tells you is if A is true, then B is true. But if A is not true, that doesn't necessarily tell you anything about the truthfulness of B. So that is why essentially there's no problem here, because these implication arrows are indeed in the right place, and there are like arrows crossing the truth boundary. But just because the previous thing was false doesn't make the next thing that comes after it false as well. It's just what it means is if this were true, then the next one would also be true.
For fans of logic gates, the meaning of A implies B is using logic gates B or not A, which is weirdly asymmetric. It doesn't treat A and B the same. And if A is false, then yep, you've satisfied this. Which I think makes people feel really uncomfortable that it's possible for a false fact to imply a false fact. And the fact A implies B, they could both be nonsense, but that's considered to be, that's okay, it passes the test, A implies B. And you can also have the one that I think really upsets people is if A is just plainly false, then A implies B for any B. Like if you have not A, then it doesn't matter what B is. So all false facts imply all facts. In terms of whether the implication is true, not whether the implication is meaningful. It doesn't measure whether the facts are related or whether the facts are correlated. Almost.
I think in like the first analysis problem sheet, I think this was like one of the things that one of the questions was about: do certain statements imply other statements? And one of the questions we spent a lot of time in this tutorial was exactly this question of like having a plainly false statement implying another plainly false statement, but the implication arrow does exist and they do imply each other. So that was very interesting.
Something someone said to me once is, well, if you want to disprove this, if you think that A doesn't imply B, you would need to find a counterexample where simultaneously an example of A and not B following on, and you can't do that because if A is nonsense, because you'll never catch a counterexample if A never happens, which feels silly. But yeah, I snuck this into the further reading notes for the automata episode. So for the definition there, and maybe if you saw this a couple of weeks ago. Inora wants to know about arrows in other directions. The way I've laid it out, the arrows all go that way, but you could draw this chart upside down or back to front, and then the arrows would be pointing the other way. I think because of my structure, they have to go that way. Good. I think this would be a fun activity for other facts. So I've taken one fact in the middle there, and I've had a great time expanding it out to 15 facts, almost all of which are true. And I could go and explore over here, I think, to say my choice of thing to put on the right-hand side for a stronger hypothesis was this thing like last digits. I could see people in chat were thinking about maybe making the primes larger or not a multiple of 5 or something to try and ban some cases to see how far they can push the implication upwards if you take a step to the right. And also I saw people trying to find, like, this step to the left was pretty devastating. Like, we got rid of this bit of the hypothesis, and that turned out to be a kind of load-bearing bit of the hypothesis, that removing it removed quite a lot of true facts. Is there something in between, or something different that we could have put on the left to explore in that direction, a kind of related fact where you just relax the condition a little bit, which is what we're going to do next week, I think, more or less. Because I'd like to talk about multiples of numbers and how really the way our proof works, if you get to it, sort of uses the fact that P is prime, but only really uses a couple of facts about prime numbers. If I see a large prime number like 97, then I could say loads of things about 97, but only a couple of facts about 97 are relevant. We use a double-sided arrow. I think so. Double-sided arrow implies single-sided arrow. So if two things are equivalent, then it's also correct to say that one implies the other. That's not a sensible thing to say, is it? Can we use a double-sided arrow anywhere? I guess we have lots of true facts, so it is correct to have some arrows pointing the other way between true facts. But I
don't know. I mean, I'm a bit uncomfortable with saying just because something is a multiple of 3, it implies it's a multiple of 12 as well. But it does work here, I guess, because they're all true.
If they're just true facts, then true implies true. So you can draw more arrows in, but we're quite uncomfortable about whether they're helpful arrows or not. There we are again on the distinction between truth and helpfulness. I think you can keep going to the right, and it's sort of multi-dimensional. There's lots of different directions you can go in. I've gone in this last digit direction, but maybe you could explore in a different sort of direction to put different things on the right hand side. There was some stuff. I guess you
could start talking about last 2 digits.
Good. Yeah. That seems like a sensible next thing to put on the right hand side. See how far you can push. See how far you can push it now. Maybe no further. Maybe 120 is the best thing you can ever say about p squared minus 1. Or maybe you can say some better stuff. I don't know, but I think the shape of it will carry on being this upward slanting line with more truth on the right hand side. Right, good. Okay, that started sounding like a homework exercise, and also we're about to hit 6 o'clock. I think we're going to call it there.
All right.
Thank you very much for joining in on the show to do prime number facts with us. People in chat are now telling us about multiples. Ooh, we've got 40, which I guess, okay. Oh, but removing the prime thing. Yeah, okay, fun times. Okay, so everything on the board says P is prime, so maybe removing that, see what happens. Could be a different direction. I was wrapping up.
I am wondering, just before the live stream started, you mentioned that you had a sort of extra question about an integral. Could I maybe just peek at that, and maybe some people in the chat could try it on their own time?
Yeah, so slightly different style of question, doesn't fit in here, but I have an integral where when you're proving things with inequalities, it's quite helpful to find something that lies in between, to find something that is somewhere in between that you can control. So on the left, I have an expression which is quite hard to get to grips with, On the right, I have the number 3 over 8. If I can find something in between that separates them, then that I will prove. If I can prove that the left-hand side is, I don't know, less than some number, and the right-hand side, it's quite easy to prove that's bigger than some number because it's just a number. But if I can separate them, that's like finding somewhere in between. That's the plan. Possibly, depending on how much integration you've seen, you can just do the integral on the left. And I'd encourage you not to, I think. See if you can bound the integral on the left. Do some inequalities with integrals. Right. There's a follow-up integration question for people. It's got the same feeling to me because it involves moving. As you try and guess what to put in the middle or where to split these apart, you try to find a kind of true fact that's also a helpful fact. And there's a limit to how far you can push it, just like there's a limit to how small you can make the number 3 over 8.
I'm wondering, would it be allowed to say that I know how to integrate 1 over 1 plus x squared? Because that feels like a harder integral, and if I know how to do that, surely I know how to do this one.
I don't know. Can you surely integrate x f of x? Yes. So some people in chat will tell us about probably logarithms. Maybe we'll do this next week, or maybe not. Maybe we'll just do modular arithmetic. Who knows? Right. Either way, we will see you again in 167 hours for another episode of Oxford Online Maths Club. Slightly scuffed my mark on that one as well. Messing up the intro and the outro, that's symmetry. Gaurav, anything else you want to mention before we wrap up?
No, I think that's all from me. Great to have you chat. It's lovely to be here, and I hope we see familiar faces next week.
Cool. Right. See you around, everyone. So it's bye from Mario in chat, bye from Gaurav, and bye from me. See you next week. Bye.